In this video, we will be discussing how do we store energy in a capacitor and how there is loss of energy on sharing charges between two capacitors. All right. So now we have studied till now that all conductors have the ability to store charge in them, and which increases the potential of that conductor. So now what we do is that we arrange a conductor in conductors in a certain arrangement to form a device which we call them capacitors. Okay. And this capacitors now has a certain charge holding ability, which is actually determined by its capacitance value. Okay, so we have studied all these things. Now we'll be finding out that how these capacitors are getting charged there. Now let's say that you're having this parallel plate capacitor, and this capacitor is connected to this power supply, this battery, and this battery is actually going to provide charges to this capacitor, because of which it will be charged, totally charged. Now when this capacitor is getting charged, so that means what happens, that the potential difference across these plates, it increases because of the charge provided by this battery, isn't it? So that means a certain amount of energy is actually being supplied by this battery to this capacitor. Okay. Now how this energy is supplied? So that means a certain work is being done, isn't it? A certain work is being done by this battery in providing charge to this capacitor, and we will be deriving that work value only, work done by this battery in providing or in supplying charges to this capacitor, and that work done is actually going to provide us that how much energy is stored in a capacitor. All right. Let's say that C is the capacitance. C is the capacitance of the capacitor in this diagram. Okay, and since it is connected to this battery, and he is getting certain charge, so at any instant, let's say V is the potential of the capacitor. Okay, so at any instant, charge Q on the capacitor that is nothing but Q equals to CV, right? So this is the charge acquired by this capacitor, who is having potential V and capacitance C, right? You can provide this equation 1. Now again, what we will do, we are going to assume that suppose dq is let's say dq is a very small amount of charge. dq infinitesimally small, sorry, small amount of charge. Okay. And infinitesimally small amount of charge is supplied by the battery. Now, initially this capacitor, before it is connected to this battery, so he is not going to have any charge. Okay, he will be having charge only if you connect it to any power supply. So once this capacitor is connected to this power supply, and when he started to acquire certain charge, Initially what we do, we assume that dq, a very small amount of charge, is supplied by this battery. Okay? So therefore, work done work done in supplying dq charge, right? And remember, the potential difference, that is constant. Potential of this capacitor, that is going to remain constant. So that work done is nothing but V dq. Alright, so this dq is the charge supplied by this battery across this potential V. Now we are going to find your net work done. Net work done. Initially dq amount of charge was supplied. Now net work done in supplying q amount of charge. Q amount of charge. So instead of writing Q, you can write here capital Q. So this is the amount of charge supplied by this battery. Okay. So net work done in supplying Q amount of charge to this capacitor. So that work done, we can calculate by integrating this. Say that this is equation number 2. By integrating this equation number 2, the net work done value can be derived. So what we do here, we are going to integrate this V dq, and that V we can derive it from this equation, which is nothing but Q by C dq. And when we write our lower limit and upper limit, now lower limit will be your initial value. Initially the capacitor was, we'll assume that this capacitor was not connected to the battery, and that is why he was having zero charge. That is why initial condition will be 0. And finally, once it is connected to this battery, and he is actually having or acquiring this capital Q charge, so we are going to write this as upper limit capital Q. We are going to integrate this 0 to capital Q, Q dq. So once we integrate, so we are going to have an expression something like this: Q square by 2 with lower limit 0 and upper limit capital Q. That means this is my final value, the final charge acquired by this capacitor. When we replace these values, we are going to have an equation something like this: Q square by 2. Okay. So next, what we will do, so our work done in supplying Q amount of charge, we have got something like this: Q square by 2C, square by C. Alright. So this work done is actually stored as electric potential energy, in the capacitor. Okay. So this work done in supplying charge to the capacitor. This work done is stored as electric potential energy. That is why we are going to use this U expression. This is the general representation of potential energy, and that is nothing but half Q square by C. Alright, this can be equation number 3. Again, we have this relation that is nothing but Q equals to CV. So this potential energy can be expressed in terms of capacitance and potential. It is nothing but when you replace this Q by this CV term, okay, so it will be nothing but C square V square by C. CC gets cancelled. So you will be having a relation in terms of capacitance and potential. It's half CV square. Right. So this is another expression of potential energy, and you can provide it equation number 4. Again, you can have a relation in terms of charge and potential. Again, what we will do, okay, we are going to write this C, which is nothing but Q by V, and we are going to replace the C value here. Q square, right now this C will be replaced by this Q by V term, Q by V. You will be having something like this, Q square of Q multiplied by V. So that Q gets cancelled, and you will be having another relation, which is half QV. Right. So you are having 3 expressions of potential energy. One is half QV, another is half CV square, another is half Q square by C. Right. So you can use any one of the 3 expression. Depends, what data are given in your equation. Depending on those data, you will be using this 3 expression of potential energy, electric potential energy. Right. So this is the amount of energy stored in any capacitor when the capacitor gets charged by any power supply. Right. Now here we will be deriving the loss of energy when 2 capacitors are connected. Okay. Loss of energy when 2 capacitors are connected. Right. Let's say that this is one capacitor, and let's say the capacitance of this capacitor, let's say it is C1, and he is having potential V1, right? So that means the charge acquired by this capacitor will be nothing but Q1, which is C1 V1, and energy stored in this capacitor will be half C1 V1 square. Okay, and let's say that you are having another capacitor whose capacitance is C2 and his potential is V2. So the charge stored by this capacitor will be E2 V2, and the energy stored will be half C2 V2 square. Right. So initially total energy represented by U, so that is nothing but U1 plus U2, which is half C1 V1 square plus half C2 V2 square. Right. This is our initial conditions. Now, when we connect these 2 capacitors, let's say that I'm connecting it using this wire, then what will happen? Certain flow of charge will take place from one capacitor to the other capacitor. Right. So when these 2 capacitors are connected, so there will be a flow of charge there, and this flow of charge will continue till the point when both the potential values of these two capacitors becomes same, right? Initially they were having potentials V1 and V2, when they were disconnected, but once you connect them, since due to this connection there will be flow of charge, and this flow of charge will continue up to the point when potential becomes same for both these capacitors, right? So connecting after connecting capacitors C1 and C2, so they will now have a common potential, right? They will have a common potential. That means potential value now for these two capacitors will be same. And let's say it is V. Let's say it is V. So that potential will be nothing but net charge. Net charge of this system by net capacitance. Initially he was having charge Q1 before connection, and he was having charge Q2. Once you connect them, there will be sharing of charge, but your net charge value will remain same. That is not going to change, isn't it? So your net charge value will be nothing but Q1 plus Q2. Okay, and your net capacitance will be nothing but C1 plus C2, because he was having initially C1 and C2. Once you connect them, so you will now have a net capacitance which will be nothing but C1 plus C2. Now remember one thing, when these two capacitors were disconnected, okay, when they were not in connected mode, so in that case your charge for these two capacitors were Q1 and Q2, but once you connect them, you will be having a different value of charge. Let's say it is Q1 dash, and let's say it is Q2 dash, but your net charge value will not change. Your net charge value will remain same. So that means this is my net charge value. This is the net charge value before connection, and this is the net charge value after connection, or in this case which will be same, right? So now after connection we are having a common potential, and that common potential is expressed something like this. Now you can replace this Q1 and Q2 value. Now Q1 is nothing but C1V1, and Q2 is nothing but C2V2, isn't it? C1 plus C2. This was the value of the charge Q1 before connection, and this is the value of charge Q2. So therefore, your final energy let's say it is U dash. So that will be nothing but half CV square. Now in this case, in case of C, you will have net capacitance, which is nothing but C1 plus C2, and now they are having a common potential, so it will be nothing but V square. This is the final energy after connection, right? Now if you replace this common potential expression, so it is nothing but C1V1 plus C2V2 whole square divided by C1 plus C2 whole square. When you cancel out this term, so you will have your final energy U dash, which is equals to half C1V1 plus C2V2 whole square divided by C1 plus C2, right? So this is your final energy expression when the capacitors are connected. Okay. So now what we are going to do, we are going to find a difference between this initial energy and final energy. So your initial energy U, so it was nothing but half C1 V1 square plus half C2 V2 square, and your final energy was nothing but half C1 V1 plus C2 V2 whole square divided by C1 plus C2. This was their final energy. And when you find the difference between these two, okay, you will have a positive quantity. Okay, so that will be nothing but C1 C2 V1 minus V2 whole square divided by 2 C1 plus C2. So if you simplify by replacing this U value and this U dash value, if you do the simplification, you will have a positive quantity, which will be nothing but this one. Alright. Now this positive quantity shows that there is there is loss of energy when two capacitors capacitors, right, capacitors are connected together. Okay. All right then. Thank you.